Hello, everybody. Thank you for dialing in. My name is Johannes Wolf. I am a medical doctor and cancer researcher. This is a teaching video aimed to explain Kaplan-Meier curves, and it is recorded on Zoom. Kaplan-Meier curves are a scientific tool to visualize the results of clinical trials in oncology cancer research. I have been asked many times to explain them, and so I made a slide deck, and this time we are recording it. We entitled this Kaplan-Meier curves. What is that? Slides in the middle are fictional. There are hand-drawn curves. I made an error in there, and I didn't fix it. I want you to find it. So please pay attention and see if you find the error. This video only gives the basics of Kaplan-Meier curves. There are other videos that come that show pitfalls of interpretation and how to make them. So here we go. This is a theoretical experiment, an in vivo experiment. In vivo means intact organisms are used. Xenograft leukemia. Xenograft means human cancer cells are implanted in an animal, and this is a leukemia model. We assume that we have a treatment. It is intravenous. The drug cannot be swallowed. It needs to be given into the veins, and we call the drug Leukemax. And we have 10 mice that had leukemia in this leukemia model, and they were treated with the drug. And unfortunately, all the mice passed away, died. Now, be assured, no animal was harmed for the data. Those data are made up. But please also realize cancer researchers in general prefer to give a drug to a human only after they know what happened to an animal. So animal experiments are reality, and I personally do think they are necessary. Now, these 10 mice in our theoretical experiment lived various times, and overall, our colleagues in the laboratory thought this is not too bad. The mice lived longer than they would have lived with the model only without treatment. And then you draw curves like that. You draw figures like that with one bar each equals one mouse, and they end up at different times. Those figures are called swim lane plots because they sort of resemble what you see when you look from the top into a swimming competition. Before you do anything further, you typically sort them with the shortest on top, and then you can draw your curve. Now, the curve is complex and is a figure, and if you have to give a elevator speech, a description within seconds, or if you have to write it down and you can't give a figure, then you need to turn this into words and numbers. The most common way to describe a curve like that in a summary sentence or word is to give it as median overall survival. The way to do this is you go to the y-axis, go to 50%, you go over to the right to the curve. Where it hits the curve, you go down, and then you read the median overall survival on the x-axis. In this case, it's 10.5 days. So the median overall survival is a time. Now, is that good? Have our researchers in the laboratory been correct that the mice live longer than a control experiment where the mice didn't get the drug? We don't know that unless we do the experiments. And the number isn't just simply the average of the numbers. It is the median. So we did that experiment in theory, and here is the curve of the controls. It is to the left of the curve of the Leukemax treated mice, and indeed, that means the controls live shorter. If we now do the same thing with the median overall survival, we have two numbers, the median overall survival for the controls and the median overall survival for the Leukemax treated animals, and one is longer than the other. And the standard way for this is called a log rank test. We're not going to go over that yet. That will be a later video. Let's go to people. This is still theoretical data. And please take into account, we're now talking about death of people. This is theoretical. but it is still very real. This is what really happens in cancer research. I have been part of taking care for children who die, and when you try to help them and you can help them, then you have to put your emotions away to think what medicine can give still. And as you have to put your emotions away in clinical care, you also have to do that in some way in clinical research. When talking about dead people, even they're not real, you have to lock away the horror that comes with this word and start thinking stone cold logic, numbers. Medical history has shown us that this is the best way to make progress. If you can't take that, or if there is you have no reason to lock your emotions away because Kaplan Meier curves aren't important for you, then just don't watch this video, because this is all about death and survival, and it is all about stone cold logic. So, having said that, this is the result of our experiment. The first patient was enrolled in the beginning of the trial, stayed on trial for 4.5 months, and then withdrew consent. That's not a good thing in a clinical trial because you lose all the following information. The second patient was enrolled half a month later, stayed on treatment until the end of the observation time, until today, and is still on treatment. Patient is doing well, a great success. Our theoretical trial is in relapse refractory acute myeloid leukemia, and we call it a phase 1b study, which means the dose of the drug has been established in phase 1a, and now all the patients get the same dose. Relapse refractory acute myeloid leukemia, if it is after all treatments that can be given have been exhausted, is a very, very bad disease. And if somebody in fact survives for more than a year, that is an extremely good. So this is what we think. This patient had leukemia treatment, bone marrow transplantation, everything that was there. And then there was no way to go, was treated with Leukamax, started after the trial, has their second patient after the trial was ongoing for 2 weeks and is still on treatment today. Third patient didn't go so well. Fourth patient went well again. And so it goes, and until patient number 10, that is the last patient enrolled 12 months after starting the trial and is still doing well, but only a short period of time. Yeah. Well, first, you need to do something that you don't need to do in the animal experiments. You all align them on the left as if they had all started at the same time. Then you align them the same way as the mice data, shortest on top, and then you draw your curve. Now, this is drawn the same way as the animal curve was before, but it is different because there are 4 patients here that by the end of the observation time were alive. This is patient number 10, the one that was enrolled last, and therefore is still on treatment at the observation time. This is patient number 1, who was enrolled first, but then withdrew consent. And after that time, we are not allowed to gather any further information. This curve is also not really a survival curve. Only if you make the bold assumption that only patients that you know and that you have documented to live lived, and everybody where there isn't the case and you have no documentation is considered to have died, then it turns into a survival curve. But that is an extremely pessimistic view, and it certainly isn't correct. I'm going to call this curve for educational purposes the pessimist's curve. It has some meaning. For instance, if you want to know how much drug you had used up, how much more drug do you need to make, this curve would give you the answer. Let's do it in a different way. This is the same figure that I showed before. The patients are aligned on the left. They're not sorted yet. We sort them, but this time we sort them differently. This time we sort all the patients that have passed away to the top, and those patients that have not passed away, or we don't know if they have passed away, go to the bottom as alive or censored data. Censored in the context of a Kaplan Meier curve is a good thing. This is the curve that you get. Now, I'm going to call this the optimist curve. It is based on the assumption that somebody, where we don't know if the patient has died, lives until the end of our observation time. That assumption is equally wrong as the other one, and I'm going to call that the optimist curve because it is the extremely optimistic view. Where do the two curves differ? Well, they don't differ among the first two patients because those patients died and we knew they died, so both curves go down. But beginning from patient number 3, you see a difference. The pessimist curve goes down, the optimist curve stays up. Until this patient, which did die, and we know it, then both curves go down. Each of the steps in both the optimist and the pessimist is 10% because we had 10 patients. Obviously, in the very end, the curves look gigantically different. The green curve looks like a very bad disease where everybody passed away, and the red curve looks like still a bad disease, but not quite as bad because you have a survival chance. Which curve is right? Well, neither of the two is right. But there is a solution. And the solution was brought by two people, Kaplan and Meier. Those are two photos of the same person, Dr. Edward Kaplan. He was a biostatistician, but really a mathematician in heart and mind. A brilliant man. He had, even in his college education, he received awards for his brilliance. And he had a career of a mathematician that's quite interesting. Naval Ordnance Laboratory, Bell Telephone Laboratories, eventually Oregon State University. In that time, he was a mastermind and developed that mathematics genius. He actually developed that not for calculating the survival of people. He developed that for calculating the lifetime of light bulbs when he was working in Bell Laboratories. This is the other person, Paul Meier. He was 4 years younger. And he was also a statistician. He stayed more in the field of clinical trials and has, after the Kaplan-Meier curves, made further gigantic contributions when it comes to randomized trials and to research in polio. Those two together, 1958, published this paper. And here in the paper is sort of the core of the mathematical answer, how you come out of the dilemma between optimist and pessimist curve. I'm not going to go over what these letters mean. If you understand what they mean, then you actually don't need to listen to this talk. I'm going to try to explain this for somebody who hasn't studied mathematics. The basis of the Kaplan-Meier estimate is that the drop of the curve, the size, how deep the curve drops, is not dependent just on how many patients died at that time, but also how many patients were still in observation. If there are only 2 patients left in the study and one of the 2 patients dies, then the curve drops by 50%. Because half of the remaining patient population passed away at that date. So every single time point calculated in a Kaplan-Meier curve is a product, result of a multiplication of how high the curve was before times the rate of the drop. Let's do this in an example. So this is our curve. In the beginning, you remember the optimist and the pessimist curves actually didn't differ. They both dropped equally by 10%. The Kaplan-Meier curve does the same. But then we have the pessimist curve drop because an observation is missing. And that happens twice. The optimist who says the observation is missing, that means nobody died. I'm going to stay up. Change is very different here. The Kaplan-Meier curve in this part agrees with the optimist curves. There is no documentation of death. There is no reason to drop. At this point then, this patient here, patient number 8, passes away. The optimist curves would drop by 10%. Here, Kaplan-Meier disagrees with the optimist curves. It drops lower because it says this death means more because there are only 6 patients left in observation. So one of the 6 dies. That means the curve has to drop by 1/6. So you multiply the 80% times 0.833, and you come up with 66.6%. That's how deep, to which point that curve drops. And then it keeps going. Now, most of the next patients have passed away, and the Kaplan-Meier curve comes closer and closer to the pessimist curve until the end of the curve, where there are, again, 2 patients that did not pass away, only end of observation, and the Kaplan-Meier curve stays as high as it was. Let's put them together. Indeed, the Kaplan-Meier curve ends up in the middle between the optimist and the pessimist curve. And this is the best accepted way of describing patient populations where the data are incomplete, where there are censored data. What have you learned today? Well, a Kaplan-Meier curve is only necessary when the observations are incomplete, censored. It then estimates the survival based on the data that are available. Median overall survival is the 50% mark. It is how much time has lapsed until half of the patients have passed away. And if you go back to this video, there is a mistake in there. I'm going to challenge you. Please find that mistake. And with this, I thank you very much for your attention. I hope you're going to come back to the next video, and I wish you a wonderful day.